Hello, welcome to today's IEAGHG webinar on the recently published study review of CO2 storage via in situ mineralisation in mafic to ultramafic rocks. My name is Nikki Clark and I'm the Senior Geologist at IEAGHG, and I'm very pleased to welcome you to our webinar today. We'll be joined by Todd Scharf, Katie Meyer and Quinn Miller, as well as a number of the team at PNNL who worked on this study, who I'll introduce shortly. Yeah, a quick note on webinar procedures for today. As attendees, your mics will stay muted throughout. If you have a question for the speaker, please add it to the chat box and we'll address these at the end of our Q&A session. Please keep them to a technical nature. We won't be circulating the slides, but the webinar is being recorded and we'll make that available on our YouTube channel after the event. I'll begin this webinar by presenting a very short overview of IEAGHG, followed by a brief background and motivation to the study. And I'll then be joined by Todd, Katie and Quinn, who will dive into the findings of the report along with their colleagues. We'll then have time for questions at the end, but as I said, please type the questions into the chat box and we'll collate them at the end of the session. Okay, the IEA Greenhouse Gas R&D Programme, IEAGHG, is an international programme that evaluates mitigation options for greenhouse gas reduction and has a programme focus on CO2 capture and storage, CCS. Firstly, a short disclaimer slide that we show at the beginning of all our presentations. So we're a collaborative international research programme founded under the International Energy Agency in 1991, but we're functionally and legally autonomous, and views are all our own. IEAGHG are a members-based organisation, and thanks to their support, we can fund our research activities. We currently have around 40 members, comprising countries, companies and organisations, and our members steer the direction of our research programme. IEAGHG helps facilitate knowledge sharing and connecting people through a number of pathways. Our main activities comprise commissioning technical studies such as this one, with over 400 studies published. You can access via our website. We hold network workshops. You can find out about these on our website or sign up to our newsletter. We host the GHGT conference, which is coming to Australia in 2026, which I'll speak about in a minute. An international summer school, and through external involvement with organisations such as the UNFCCC, IPCC, London Convention and ISO and others. If you're interested in our summer school, the applications open around December, January time. And as I mentioned, GHGT will be coming to Perth next year in Australia, and call for abstracts are now open for this with a deadline of January. So moving on to this study that we're going to be looking at today, the review of CO2 storage via in situ mineralisation in mafic to ultramafic rocks. As a bit of background, mafic and ultramafic rocks are very widely distributed globally, and they offer an alternative storage opportunity for permanent CO2 sequestration compared to storage in conventional sedimentary basin settings. And recent field experiments have begun to demonstrate the potential that largely rely on rapid in situ mineralisation of injected CO2. IEAGHG and its members felt it was timely to commission a critical evaluation of the technology at this point to understand progress and what is necessary to scale up to industrial volumes necessary to impact climate targets. So the objective of the report is to evaluate progress, barriers and knowledge gaps, and to provide stakeholders, regulators and investors with a comprehensive summary of current knowledge and understanding of subsurface carbon mineralisation in mafic to ultramafic reservoirs. So the study was conducted by the Pacific Northwest National Laboratory, led by Todd Scharf and his team, who will be up shortly to present the findings, and they are listed here in the order that they will present. The study was widely reviewed by 15 expert reviewers from 8 organisations, and it generated a lot of feedback for the team, and I'd like to thank them personally for their professional approach to dealing with all the comments. The report was published for our members in August of this year and will be available for the public in February in 2026. So I will hand over now to Todd and Katie to kick this off, and then over to Quinn, and then the rest of the team here who will be presenting on the reports.
Thank you very much for the introduction. And I also want to thank the IEAGHG for the opportunity that they gave us to develop this report and to also work on a topic that is extremely important to this research team. As many of you know, we've been involved in CO2 mineralization and ultramafic reservoirs for several decades now. And we've contributed heavily to that body of literature. And we felt it very important that we work on a study like this one right here that really gave the state of the art. Where are we right now? What is happening? And what are those gaps and those opportunities that exist as we move forward? So I also want to thank all the people that took time today to join us and to listen to an overview of the report. You will have a treat here in just a minute. You get to hear from every single member of the report. There's going to be different chapters presented by each member, and you'll get a really good feel for what this report does and a good highlight of those gaps and those opportunities. But before we start that, I would like to give a few minutes to Katie Mueller, who was the project manager for this report and managed the process, which was done in about 6 months. So Katie, could you give us some insights on how you dealt with the challenges of bringing a large team together and completing this task within the required timeline?
Well, thanks, Todd. And I'd like to give a little overview of the process. This report came together over about 6 months of work, with the first 5 being gathering of information, writing, compiling the report, and then the last into review. During this time, we had up to weekly meetings with the team to push the document forward. And this really was a team science group effort. We had section leads driving each of the different chapters, but all the individuals on the report worked a lot on it and substantially contributed. That involved not only gathering from the literature and what was published, but talking with people, communicating with experts across industry and academia. We also worked with the PNNL graphics team to try to translate some of the concepts in this report into graphics. This was very much an iterative process between the graphics individuals and the team here that resulted in the original graphics you see in the report. This, by the end, became a very large document with hundreds of references, nearly 400 in the end. And we put a lot of work and iterative into making the report flow together, shifting sections around to the cohesive document that you see. Our final phase of this were review comments back provided by IEAGHG. This consisted of almost 700 review comments from 15 reviewers. So we are very grateful for those. And we again came together as a team to address those and compile into the final report you have in your hands. So we're grateful for the opportunity to do this and to come together as a team. Thanks, Todd.
Okay, and we'll take 1 minute here for acknowledgements. A special thanks to Nicola Clark for managing the production of this review. She was very helpful to us, met with us many, many times. And also, as you've heard before, we had 15 expert reviewers. They gave us a lot of comments, a lot of good comments, actionable comments that the team was able to jump in and make this report much better. So we could not have done this without our reviewers, and we just can't thank them enough. There was a lot of time spent on this report by the reviewers, and we acknowledge that, and we did take those comments to heart. And then we also want to thank our science and industry experts that took time to meet with us and let us interview them and talk to them about things that went into the report. We could not have done this without you. You were super helpful when it came to understanding some of the challenges, understanding the state of where these field pilot studies are and what we could expect to happen in the next 5 to 10 years in that space. So again, a big thank you to both the reviewers and to those science and industry experts. And so now I'm going to hand this over to Quinn Miller, who's going to manage the rest of this presentation and walk the team through each chapter of this report. Okay, Quinn.
Okay, thank you, Todd. Yeah, so I'll first provide a brief overview of the presentation, and then we'll hear from the rest of the team. And these are the different sections that were included in the report. And we'll step through it slide by slide and provide that overview. And then, and then after conclusions, we'll have time for Q&A led by Nicola. Okay. So this is a team that was assembled for this report. You'll get to hear from most all of them today. And a lot of interdisciplinary skill sets were applied to meet the deliverables for IEAGHG. And it includes geologists, geochemists, chemists, permitting, upscaling experts, all sorts of earth science expertise and project management went into this. And I also want to point out a lot of early career researcher talent, and it's part of the pipeline we've developed at PNL for subsurface geochemistry and subsurface in general. And a lot of the people on this call and who you will hear from today have worked with PNL prior to them coming here as part of their education. And so, okay. So to complement the earlier overview of what this report is about, we focused on in situ mineralization. So overall, this describes the technologies that leverage the downhole conditions of elevated temperature, pressure, different fluids, different reactive rock lithologies in these subsurface systems to accelerate carbon mineralization and accelerate the permanent storage of injected anthropogenic CO2. So again, focusing on subsurface. And these are mafic and ultramafic rocks like basalts and peridotites, which are globally widespread on continents and offer an alternative to conventional sedimentary basin storage. And in this case, we're relying on rapid in situ mineralization down in the subsurface. So in this report, we aim to evaluate the progress, barriers, and knowledge gaps in order to best inform stakeholders and help scale this up to industry relevant volumes. And in the next slides, we'll provide a key analysis across the geology, geochemistry, risk monitoring, and permitting, and how that all feeds in to understanding the overall view of carbon mineralization. And on the right here, here's an example of a schematic we worked on and included in the report showing, in this case, a layered basalt system, so a mafic rock with different injection horizons, and how deep, for instance, at Wallula, the PNL test site, the CO2 is injected at 800 meters deep or more. So far below any typical drinking water resources. Okay. And next, I want to give the floor to Nora Lopez Rivera.
Right, thank you, Quinn. Hi, everyone. My name is Nora, and I will be going over section 2, which is titled Screening, Simulation, and Field Studies. So for this section, we compile global work on CO2 mineralization and mafic and ultramafic rocks, and we focus on 3 main areas, which were screening, simulation, and field studies. Excuse me. So for our screening studies, we estimate storage potential based on reservoir properties, such as porosity, mineralogy, and rock volume. We found from these studies, from approximately 20 studies from over 10 countries, these primarily focus on basalt formations, and they use different methods in this study. They vary from mineral replacement to partial mineralization. But overall, we found that global estimates range between 2.5 to 4.8 teratons of storage capacity. As for our simulation studies, these use reactive transport modeling to predict the behavior of CO2 injection in the reservoir. We identify approximately 31 studies across 11 different sites, across 5 different continents. These model mafic and ultramafic systems, and they use tools and different codes such as self-react, stomp, flow, tran, front flow, and among others. Now, for model accuracy, we found that this heavily depends on the use of formation properties such as rock heterogeneity, mineral volume representation, mineral kinetics, and surface area, among other key formation properties. As for our field studies, these provided real-world validation. So far, roughly 100 tons of CO2 have been injected globally, mainly at Carbfix in Iceland and the Wallula basalt site in the United States. These projects, field studies projects, demonstrated rapid mineralization, often occurring within years. This is significantly faster compared to mineralization processes in other reservoirs with different lithologies. And the overall key message of section 2 is that CO2 mineralization in mafic and ultramafic rocks hold significant potential for secure and permanent storage. However, large-scale deployment will definitely depend on standardizing storage resource estimation methods, improving mineral kinetic data, and expanding field scale validation. And with that, I will pass it to Emily, who will go over section 3.
Hello. So for section 3, we evaluated the reactions used in these simulation studies and their relevance to CO2 mineralization in the subsurface. So our first consideration here was the method by which CO2 is injected into the subsurface. We have an overall schematic shown here where we can inject aqueous CO2 all the way to our supercritical CO2, with many opportunities falling between these two end member conditions. From these 31 modeling studies mentioned by Nora, we compiled the relevant mineral phases and the reactions used to describe their dissolution and precipitation kinetics. Though there were 70 mineral phases, give or take, we could broadly categorize these into a few key top phases that need to be accounted for. These included calcite, glass, plagioclase feldspar, and pyroxenes. Some of these phases modeling studies additionally included other secondary mineral products, other minor phases, but these were some of the major ones to account for across these mineralization simulations. From this evaluation, we find, though, that there are unexplored key controls that will likely need to be accounted for when pursuing further simulations to accurately predict CO2 mineralization and location. These include silica-rich passivation layers that can form over time, the presence of secondary minerals that pre-exist the CO2 injection. These are such as your zeolites and clays, as well as organic and inorganic carbon reactions. So, for example, the role of microbiome within the subsurface. Some of our key takeaways as we pursue a commercial deployment of subsurface CO2 mineralization. These kinetics that are listed in literature, there needs to be a field validation for them. This calls for more field data to understand if our model predictions are truly accurate. Many of these studies where these kinetics were parameterized and these reactions were parameterized are on single mineral phases in laboratory-based settings. We also need to think about tailoring these injection strategies that I mentioned at the beginning of this slide to fit the specific site hydrogeology and water constraints and the geochemistry of that site. So with that, I will hand it off to Stephanie.
Great, thank you, Emily. My name is Stephanie Dorado, and I will be talking about Chapter 4, Subsurface and Risk Evaluation. As Emily just mentioned, field-validated kinetics are critical for accurately predicting the behavior of fluids in the subsurface, especially reactive fluids. And these model predictions rely on detailed and site-specific characterization. Characterization mafic-ultramafic rocks really aims to look at highly heterogeneous pore volume networks, which you can see in the figures on this slide. And characterization is also looking to evaluate chemical properties such as in situ fluids and secondary minerals, which you can see circled in white on the hand sample as an example of a in-place secondary mineral. So this is really key to understanding altered pore space as well as reactivity over time. And when we think about what it looks like to characterize these rocks in a traditional, drilling a well, taking core, doing core analysis, collecting fluid samples, a lot of those same techniques can be used here. But really what we found was that additional care is needed when we look at hydraulic testing, geomechanical testing, and geochemical characterization. For example, hydraulic testing, we may want to test for longer periods of time to really accurately understand the in situ fluids, as well as understand flow in fractured media to make sure we have a representative baseline. We also have to really look at non-mineralization trapping mechanisms, and we need to evaluate those because prior to mineralization, early injection stages rely on solubility structural stratigraphic trapping. So we need to look at all of the trapping mechanisms just like we would in a standard sedimentary CO2 environment. In terms of risk, mineralization storage evaluation is largely the same as looking at risk in a sedimentary basin. In addition, we're really looking at the injection of fluids in the subsurface, that as we inject fluid in the subsurface, pressures can change. And in the case of mineralization, we're also looking at alteration and the evolution of pore volume over time, which can include dissolution and precipitation. So when we're looking at risk, we need to consider what those changes look like. And that's really based on modeling. It goes back to the modeling and the characterization. Our report found that projects to date have not reported reduction in porosity as a result of mineralization, but they do attempt to calculate mineralization effects in terms of storage capacity over time, which Nora mentioned is still an ongoing area of research. And we also have to think about specific injection strategies in terms of risk. And so as Emily was mentioning, we have an opportunity here to evaluate and optimize the way that we inject fluids into the subsurface. And if we're thinking about how risk comes into injection strategies, we need to think about operational uptime, the number of injection and monitoring wells, thermodynamic effects of cold CO2, and geomechanical implications and water use. And with that, I will pass to Matt to discuss.
Thanks, Stephanie. Hi, everyone. My name is Matt Valenti, and I'll be discussing the monitoring section of the report titled Monitoring for CO2 Storage in Mafic and Ultramafic Reservoirs. So I'll start by giving an overview of the key monitoring objectives, which broadly are quantifying stored CO2, verifying sealing or containment capacity, risk identification and mitigation planning, validating model conformance, regulatory compliance, and operations optimization. So broadly as a whole, monitoring has a very important piece of the overall carbon storage puzzle in that it functions as both a safety and risk mitigation approach, but also part of your operations optimization and performance improvements. As my colleagues discussed previously, there's multiple end members for injection strategies, and different site-specific conditions will always impact your monitoring program. However, the monitoring strategy should always reflect the primary trapping mechanism for that project. So for example, depending on the injection strategy, if you're using free phase or supercritical CO2 versus aqueous CO2, your primary trapping mechanism will either be structural or stratigraphic trapping at first, or solubility or mineral trapping over time. And so depending on that, your monitoring techniques employed might vary either over the whole course of the project or even during time throughout the project period. Finally, depending on how fast you expect mineralization to take place, which could depend again, as Emily discussed, the kinetics of the rock, the fluid composition, and overall just the reactivity of that reservoir, then you might expect to use different techniques to capture that mineralization fingerprint, so to speak, over time. Finally, what we've seen from the field pilot projects and other studies that, for example, Nora discussed from section 2 of the report, is that many of these mineralization projects are more reliant on geochemical monitoring techniques compared to geophysical techniques, so that we are able to actually characterize and quantify the mineralization that is taking place. So what this means is that our monitoring programs typically rely on rock and fluid geochemistry data and the use of different types of tracers like reactive, non-reactive, and isotopic tracers, which can clue us into the different mineralization reactions that are taking place in the subsurface, and also understand more about the flow paths in these sort of complex, typically fractured reservoirs that Stephanie was discussing. So what I want to kind of reiterate here is that while geochemical tools are more commonly used in the pilots, so for example, the Wallula Basalt pilot project that PNL led used a lot of geochemical tools to confirm that both the fluids were indicating a saturation of carbonates, and that was confirmed with physical samples of carbonate materials retrieved from sidewall cores. At the carbon-fixed sites in Iceland, they were using tracer tests to basically indicate that the geochemistry was changing, indicating precipitation of carbonate materials. And so we can use all of this data in comparison with the geophysical data from things like logging, surface measurements, et cetera, to really understand how our reservoir is evolving in a reactive regime in the subsurface. So the graphic on the right is a generalized depiction of what a monitoring plan could look like for a hypothetical storage site, where we have a mix of different types of wells. So the injection well, in-zone monitoring wells, above-zone monitoring wells, and then also groundwater monitoring wells. These can all be used for different types of physical samples, but also for geophysical logging to complement the surface geophysical logging that's presented on the top of the figure. And so finally, the key takeaways from this section are that fit-for-purpose techniques and technologies have been developed through the different field mineralization projects, and that these have shown that we should build our MRV around geochemical monitoring so that we can have data that can tightly couple our measurements to those models that Nora was discussing for reactive pathways, so that we are able to quantify not just the physically trapped CO2, but also the chemically trapped or mineralized CO2. And finally, regulatory requirements indicate that a risk-based monitoring program will always be required, and that project risks are always going to be site-specific and will need to be considered and integrated from the pre-construction all the way through the post-closure phase of the project. And so a bit more about the regulatory requirements will be discussed now as I hand it off to Ellen.
Thank you, Matt. So in section 6 of the report, we go over the global regulations and legal barriers for CO2 storage. In the report, we have a nice table that has a compilation of the guidance and regulations from 10 countries, and it's non-exhaustive. And from those 10 countries, we do look at a few different governing agencies within those. So go check out the reports, great table. But within that section, we kind of drill into the US EPA Class 6 well permits and the EU CCS Directive Guidance 2 document. So the US EPA Class 6 is specifically for sedimentary basins, though basalt is recognized. However, there are no prescriptive requirements for mineralization in reactive reservoirs. Within the US EPA Class 6, geochemical modeling is strongly encouraged, but it is not required. And applicants who are injecting into these reactive reservoirs may be eligible for a shorter time of their post-injection site closure timeframes. From the US CCS Directive Guidance 2 document, this is a non-legally binding guidance document that is specific for mineralization projects. So within that guidance document, the recommendation is that the CO2 is injected in the dissolved aqueous phase, and it remains in that phase until mineralized. With that, there comes recommendations for the pressure temperature regimes and for geochemical monitoring that couples with that aqueous CO2. And within this guidance framework, there is no requirement for a caprock. Containment can be demonstrated without one. So overall, in our review of these frameworks and regulations, they exist, but they're ever evolving with new pilot studies, with new commercial injection plans, but there are no outright regulatory barriers really that were identified or protections. And with that, I will pass it on to Heath.
Thank you, Ellen. Today I'm going to be talking about the scale-up and cost analysis for in situ mineralization on mafic-ultramafic reservoirs. And I'm really going to be drawing, this section really draws a lot on all the previous chapters in order to better understand what are going to be some of these, some of the considerations that you're really going to need to understand for scale-up. So the challenges really span geomechanics, which we heard from Stephanie, so really understanding changes in pressure due to mineralization, as well as seismic activity and fracture evolution, as well as the geochemistry, as you heard from Emily. So understanding your stream compatibility with your specific reservoir of interest, as well as secondary mineral clogging, which has not been shown in field sites yet, but larger, more industrial volumes, that definitely becomes a consideration. So then also understanding your pore space management, as well as the public perception. So really doing stakeholder engagement to better understand and better inform the public on in situ mineralization, as well as some general logistic and techno-economics, and the monitoring, reporting, and verification that you heard from Matt about. So some of the big scale-up considerations that really need to be considered are water, energy, transport, and pressure, as I mentioned earlier. So for water, you really need to understand your site and water availability as specific to the aqueous injection method. You need large amounts of water. Just as an example, Coda Terminal in Iceland estimates they're going to need about 3,000 liters per second for their 3 million metric tons a year scenario. And so that might obviously not work in all regions. So then understanding which specific injection method you may need, whether it's a supercritical CO2 or aqueous CO2, or just somewhere in between that with the water alternating gas methods that we mentioned, may be something to take into consideration dependent on your site. And but I guess as a pro, with mineralization, if it's accurately modeled, the footprint and the area of review, as well as the post-injection site time closure may shrink, which would thus improve the economics. But yeah, overall, the core scaling factors include water sourcing and handling, as well as your pressure and conductivity measurement when injecting into these formations, as well as looking at your injection strategy of choice, whether that falls on one of the end members or is somewhere in between. And this will ultimately help trade your wells and CapEx costs against your operating management and water. And with that, I will pass it on to Navajit.
Thanks, Heath. My name is Navajit Lahiri. I'm going to talk about some of the challenges and really the opportunities for carbon storage in mafic and ultramafic reservoirs. So one of the key challenges is the economics around carbon storage. And for this, we really like to look at the Earth as a reactor approach, where carbon storage is one part of what we do, and we're able to get co-benefits along with carbon storage. For example, recovery of critical minerals, and also stimulated geologic hydrogen. Also, having validated mineralization models for carbon storage will lead to reduction of the area of review of post-injection site care, and thus help in the economics of carbon storage. Also around MRV, there exists challenges where some conventional CCS monitoring, reporting, verification methods are not very well suited to dissolved or phase changing or supercritical CO2 injections. This is where we would want to involve reactor transport, coupled MRV, or advanced sensing technologies that can cut monitoring costs and shrink the area of review of post-injection site care for carbon storage. And with any carbon storage effort or any injection effort, there exist challenges with injectivity. And for this, as others have mentioned here, Stephanie has also mentioned, and Heath has mentioned some of our other approaches where we can look at water alternating gas or microemulsions or other novel injection approaches to mitigate some of those risks. And so some of the key takeaways here is that targeted innovation can turn challenges into opportunities and mitigate some of those economic risks. And also looking at mineralization-specific carbon storage and developing toolkits around that, since current carbon storage that is widely applied in sedimentary basin. With that, I'll hand over to Quinn.
Okay, yeah, thank you, Navaji. And just to wrap it up with the conclusions and outlook of the team and what we're saying in the report is overall limited experience so far poses scaling risk. However, we have ongoing learnings from current and future and past field sites, and there's more good stuff on the horizon, both on the continent and out in the ocean. So a lot of excitement there, and going to be a lot of knowledge gaps that will be addressed in the future. And this will create an overall better understanding of in situ mineralization in these complex reactive reservoirs.
Thank you very much. Thank you, Quinn, and thank you for all the team there for doing such an amazing job at going over the contents of the report in such an efficient way. Thank you so much. Just a note to anyone, we'll be going into our Q&A time shortly. So if you have any questions, I think people have started putting them in the Q&A box. So do feel free to type them in there. So yeah, so I think Todd is going to be delegating which member of the team answers which question. So I will start with Alexander's question here. So which software was used for the mineralization simulation studies? Yeah. You need to unmute yourself, Todd. You're on mute, Todd. Look, don't look. Don't pass it. Todd, sorry, you're on. I do apologize to everyone. You'll need to unmute yourselves. Yeah.
Yeah. Hi, can you hear us now?
Yeah.
Okay. Hi, how's that? Can you hear us, Nikki?
So the question, did you get the question? Which software was used for the mineralization simulation studies?
Quinn, can you, are you able to see if Nikki can hear us?
Yes. Yeah. Can you hear us okay in the room?
I can hear you now. Yeah,
Okay.
I couldn't hear you before.
Excellent. So through this.
So you can,
Okay.
Nora, or you can answer that question.
Okay, yeah, so I'll pass it off to Nora to talk about overall, there's a mix of different reactive transport approaches that were taken in literature and reviewed and compiled. So Nora?
Should I turn on my?
No, just talk to
Oh,
this.
yeah. Hi, so there are different parameters that should be considered for these type of modeling work. These have to be formation property parameters, so things like mineral volumes, mineral surface area, any kinetic data, porosity, permeability. Honestly, for modeling simulations, the more the merrier. The point is to use the most accurate data that is available. This could be from lab experiments or from field studies, but the main purpose is, again, to have really representative parameters and data that we use for these simulations, and that way we can have more accurate results. So it's definitely ongoing.
Thanks, Nora. I think the question was which software was being used for the simulation for this.
So it depended on the study, but yeah, there's different codes and different softwares out there. They're really tailored also to either the national lab or, for example, national lab in Berkeley uses a lot of CrunchFlow. Here we use pFlowTran. So it depends, on the lab. It depends on what you want to simulate as well. These codes and simulation softwares sometimes can be used for different types of simulations. So it really depends, but there's many out there. And I think we list a lot of them in our report.
Yeah, I seem to remember there's a table. Thank you, Nora. Okay, so next question we have. In the report, have you considered how rock reactivity is measured? Could a standardized protocol be developed so that all studies speak the same language?
Yes, I'm going to hand this over to Quinn, who is working extensively in this area.
Yeah, so short answer is yes, absolutely. In terms of making a standardized protocol for assessing reactivity, and we do talk about reaction extent and how to calculate that, and how to calculate rates and report rates, and making sure everything's in a common kinetic and thermodynamic framework.
Thank you. Franz, I see your hands raised. I think it's best to put the questions in the chat box and I'll be able to, can't unmute you, I'm afraid. Okay. Yeah, so as you mentioned, the co-benefits, so this critical minerals and hydrogen, is any progress regarding this critical minerals? What kind of critical minerals are you looking for?
Yes, so currently in, for instance, ultramafic rocks, there's been a lot of attention, including on multiple projects here at PNL, looking at, for instance, nickel and cobalt in olivine. And so that would typically be considered, a country rock or gangue or non-economic as in a traditional ore deposit sense. But these rocks are widespread, and if we are stimulating them with reactive fluids and doing some downhole in situ recovery and in situ separations, that could be a co-added benefit. Yeah.
And I will add to that response. This is actually an emerging field, and there have been several studies here and programs in the United States that is looking at the possibility of co-production of these rare earths and critical materials and minerals. So the ARPA-E minor program is a good example of that. You can look that up on the internet, but that was focused on looking at nickel and cobalt and perhaps even copper. But stay tuned. I do believe this is an exciting area of research, especially as we move forward, looking at different ways to get more value out of these types of formations.
Great, thank you. I'm going to pick. There's lots of questions. Thank you so much for all your questions. I'm going to talk about, so regarding, this is from Sebastian Fisher. Regarding site characterization and especially identifying storage capacities based on seismic surveys, how can this be done for mafic-ultramafic reservoirs? Seismic studies cannot, as Jens understands it, cannot differentiate between porous and impermeable layers in mafic and ultramafic layers. Can you please comment on this? Are there alternative methods available?
Okay. So I'll turn that over to Stephanie to talk about application of seismic and other alternative geophysical methods for helping understand reservoir characterization and knowing where the target zones would be.
Sure. Can you hear me okay? I'm across the room, the laptop. And I've got my camera on, so I think so thank you for the question. You're correct. Seismic characterization in basalt is tough. And it's something that, you know, over the last couple of decades, we're actually seeing more promising results. Seismic sampling, VSPs, wellbore surveys, and things like that. And really, there's some work done in Brazil actually recently to characterize basalts. And what they're seeing is promising results using low frequency. This is 1 to 1.5 hertz, high density surveys. And so we're not ruling out seismic just yet, and it's getting better. But traditionally, the way we understand storage capacity in basalts, basalt specifically, is through well testing. Good old fashioned, we drill a well, we look at the thickness of these interflow zones. These interflow zones have porosity and permeability not dissimilar to karst and carbonate formations. And so we're talking about Darcy perm flow in these intraflow zones. But we have this stacked reservoir, right, which is essentially 100 individual basalt flows in between low porosity, low permeability seals. And so when you think about storage capacity, you can come at it from a traditional pore volume estimation, but then we also need to consider mineralization. And so reactivity potential, surface volume, surface area, and reactive potential over time. And so it's an area of continued research. But yeah, in general, seismic is also an area of continued research where we're getting better using novel techniques. Thanks.
Thank you very much. So I saw a question. So a question from Neeraj Gupta. Outside of Iceland projects, are there any commercial projects in planning design stage globally?
Okay. Yeah, we'll have Heath speak to that. And
yes, there are actually quite a few commercial projects that are currently in planning. There's, I think in the report, in Nora's slide, we outlined there are about 17 projects around the world that are in sort of that planning to inject phase, with a lot of projects that are have already drilled wells and are preparing for injection. And that was some great information that we actually got as we discussed. Those industry experts that we talked to, they were informing us of some planned injection sites around the world. And so we were able to capture those in the report, and you can read more about those there.
Thank you very much. I saw a question from, trying to hop between the chat and the Q&A. Okay, so let's say from Paul Zikor, what type of injection rates and max storage capacity could we expect from a typical mafic-ultramafic storage site field?
Yeah. Okay.
Go ahead.
Oh, yeah. So definitely variable. We do compile those in the report, but it depends on obviously the amount and how many wells and the lithology. So I think, Todd, do you want to speak to that a bit?
So that does have a lot of variation, especially depending on what form of CO2 you inject, whether it's aqueous dissolved or supercritical CO2. That will tell you how much you can actually put in your reservoir. But for a good example, the Carbon Safe program here in the United States was targeting 50 million metric tons of carbon dioxide in a 30-year period. So that really does set a high bar. It is a commercial scale injection strategy. And the only way that we can really drill down into that is to have our characterization wells. And that's part of the Carbon Safe program. Drill your stratigraphic well, do your hydraulic testing, and understand your flow rates and your injectivity.
Thank you, Todd.
Great. Okay, so I'm going to bring up it's been asked a couple of times about the sealing formation. So in some instances, the definition of a sealing formation is required. A lot of research has been focused on injectivity and capacity, but what kind of considerations are needed for identifying a seal unit for these types of systems? Intraformational, I think intraformational.
Yeah, so as Stephanie mentioned, and as Todd mentioned too, ideally you have a characterization well where you can perform hydrogeologic testing on the units and also get water samples and other samples to understand, for instance, in the Columbia River basalts, where about 2/3 at least of the stack is the sealing formation part of the basalt stack. You can figure out how impermeable they are, what their fracture networks may or may not be like, what the joints are like, and also based on different gas and isotope sampling, you can understand their geologic isolation over time from other stacked flow tops. So definitely the more subsurface characterization, the better in understanding your reservoir seal system.
Great. And then I have a question. So in the risk section, we didn't discuss seismicity, induced seismicity. Is the risk of induced seismicity any less or greater for a mafic-ultramafic formation? What would you do to mitigate it? Or would it be sort of similar to what would you do in a normal sedimentary formation?
So it is very similar to what you would do in a sedimentary formation. And the key here is to make sure that you have a very well-defined characterization plan. The more information you know about your reservoir, the more characterization data you have, and the more simulations that you can conduct, the more accurate simulations you conduct, it is the best way to lower your risk. Understanding what's happening and understanding the ability to predict what's going to happen is super important. And on top of that, having a very good monitoring plan that starts before your carbon storage project begins. Having that baseline data and understanding what's actually happening in the region and in the area will just inform your decision making much better. And keep an eye on these things as your carbon storage project evolves. Understanding that you have to have some type of mitigation in place if you start to detect any type of seismic activity.
Okay, thank you. Right, so we've got a question from Parjot Pawar. What kind of timeline do you think we're looking at before mineralization becomes widely used?
Okay, in terms of adoption?
Adoption, I think, take up, yeah, and maybe on a
okay.
more commercial scale.
I think as Heath pointed out, with different stages of operation and operational planning, it's going to be diffuse over from present to, I think, the next 20 years or more. So it's hard to estimate an exact timeline. But Todd, you have some comments about that?
So these are actually exciting times. We have global interest in CO2 mineralization projects. As you heard from Nora, there are multiple projects that are occurring. Some are just starting up, some are a little bit further along. But what I think is most exciting right now is that there is interest to gather more energy products out of these types of formations. So if we start to see more interest in critical material recovery or stimulated geologic hydrogen, that is only going to enhance our knowledge on these formations, on how to put non-native fluids into these formations, how to engineer those fluids to give us those products we want, whether it's CO2 mineralization or it's nickel or it's hydrogen. So I'm very optimistic. I think we're going to see huge gains in the next 5 to 10 years in this space, especially with some of the field sites that are already operational. And the Carbfix team is actually deployed here in the US. So there are going to be more and more pilot studies come online, and more and more interest will grow as this type of technology matures.
Yeah, thank you.
That's fantastic. Thank you. And I think on that note, I think we will just like to thank everybody for their contributions today. So maybe if the team would like to put all their cameras on, we'll see all of our contributors.
We are sorry we had problems in the room today. We apologize for that.
No, it's worked very well. And I think it was about 2011 that IEAGHG did a short paper on CO2 mineralization in basalt. So this was a timely review, and hopefully in the next maybe 5 to 10 years, we'll be able to do another report and see the progress that's been made in that time. So Todd and Katie and Quinn and Nora and Emily, Stephanie, Matt, Ellen, Heath, Navjot and Quinn, thank you very, very much for today. Thank you for producing such a great report, and thank you for everybody for joining in. And I'm sorry we didn't get to all of your questions, but thank you very much for engaging with us today.